your presentation, okay? Try to say something to make sure that the sound is working.
Working.
Yeah, we can hear you now. There's something wrong with your camera, at least on my. You seem like blinking your face. So maybe are you using some kind of background? Klaus? I don't know if you are speaking now. We cannot hear you. It seems that either low bandwidth or CPU problems with your computer.
Okay. Can you hear me now?
Memory. Yeah, we can hear you now. Yes, I think it's better by turning off your video,
the video.
Your webcam.
I switch it off. Camera.
Yeah, that's better. We save some bandwidth. So
I will do.
Yes, you can. We can see your screen. We can also see your mouse. So if you want to highlight something from your presentation, you can move your mouse. Okay. Wonderful.
I try to switch. Be careful. Scheiße. Schließen. Ich weiß nicht, ob das geht.
Can you work with the slides? Can you go forward and backwards? Yes, Klaus? We cannot hear you now. Your camera is again on.
Yes. Yeah. Video stoppen.
I think, it's better to switch it off. Yes.
Yeah. So now I've switched off the camera and I hope you can hear me.
We can hear you now. Yes, that's perfect.
Then I will try it again.
I will be helping you during the workshop with the whatever problems you may have. Your camera seems to no. Your camera is off. Yes.
Off, and you can hear me.
Yeah. And I can see. If I stop hearing you, I will let you know somehow. Okay.
Okay. And you can see the presentation.
Yeah, the first slide with the.
Okay.
That's it.
Then we are good now. Yeah.
Yes, excellent.
Maybe I start, or would you like to?
You can start now. Yes, normally we try to start in time. Yeah, to avoid delays. So you can start now. Don't worry.
Yeah. Okay. Good. So my presentation will be about our Neumann ESSA hydraulic compressors know-how. Many people of you won't know that we are one of the reciprocating compressor manufacturers acting globally. So our main business is big reciprocating compressors mainly for hydrogen application. The reason for that is pretty clear. The hydrogen is that gas which can reasonably only compressed with a reciprocating compressor. All the other principles like turbo compressors, screw compressors are more or less not appropriate for hydrogen. We have many applications, low pressure, medium pressure, and high pressure, and I will go just through all the possibilities of compressing hydrogen with my presentation. I give you some ideas what challenges and limits we have when we apply lubricated reciprocating compressors for hydrogen. Just to introduce, we have the possibility to compress the gas lubricated or non-lubricated. The non-lubricated is even possible for many years, let's say minimum 30 years, due to the development of PTFE with special fillers as the piston and rider ring material. With these modern plastic materials, we are able to do it also non-loop, but in some of the applications, lubricated surface is mandatory. Here, especially the refineries. The refineries ask always for a lubricated compressor, since they would like to run the compressor minimum 3 years without any interruption. So 3 years, 365 days, 24 hours. So they need the compressor all the time, and therefore they prefer the lubricated service, because for lubricated service, the wear of the rider band and piston rings is neglectable, and therefore they can run the compressor for a longer period of time. Yeah, some design aspects in our world. We work in accordance with the so-called API 618. API 618 means American Petroleum Industry. This is a group in the United States which creates guidance for all equipment used in refineries, and the 618 is the one for the reciprocating compressors. There are also guidelines available for turbo compressors, screw compressors, gears, and for our business it is the API 618. There are a lot of rules in that which is mandatory to fulfill, and I give you one of the most important, which is the maximum allowable discharge temperature. So in the 5th edition, which is the currently valid edition, we are allowed to go up to 135 degrees C as a discharge temperature for each stage. This is a limit, and this creates for higher pressure differentials the numbers of stage you have to use. In the 6th edition, which is not yet released but will come, we even reduced this limit to 125 degrees C. I know that very well, even though that the edition is not available yet, since I'm member of this working group. So I worked in the group to develop this 6th edition. So therefore, that's the reason why I know what will come. Yeah, we have experience up to 500 bar, but hydrogen, there are applications for hydrogen not only in the mobility sector, but also in the chemical industry, where you need hydrogen compressed to pressure above 400, at least 400 bar. When you have such high pressures, then one tricky thing you have to be careful with is the so-called rod load reversal. I will explain it later. And for big compressors, when the diameters of the cylinder becomes very big and the load becomes very high, then a special rider band and piston ring design is needed to avoid issues connected to this lubricated service. I will explain. Here is an example of our design program for such a high pressure compressor. High pressure means when we are definitely above 200 bar discharge pressure. In this case, it is 480 bar. So this is an application in the United States for the chemical industry, where the compressor was designed for 480 bar discharge pressure, and suction pressure was 240. We designed the compressor according to this sketch. So we have a two-stage compressor. The first stage was on both throws was arranged in direction of the frame, and the second stage was arranged in direction of the cylinder head. In between, between the first and the second stage, we have a so-called balance chamber. It's clear from the second stage, we have leakage flow into this room, and from the first stage, we have leakage flow into this room. And in order that this does not create any pressure in that room, we connect this room to the suction side of the first stage. So on this surface of the piston, you have always suction pressure first stage. The reason for this step piston configuration is pretty easy. We would like to protect the packing. The packing is at the end of the crankhead side of the compression, and the packing has to seal the gas against the atmosphere to the frame. And here the pressure limits are more restrictive compared to the pressure limits on a piston. So the packing is, in terms of lifetime of the packing internals, much more critical than the piston rings. Piston rings can be designed for higher pressure differentials easily. And that's the reason why we choose this special cylinder and piston design, just to protect the packing from the high pressure. That means in that case, we have 240 bar discharge pressure, and this is a maximum pressure acting on the packing, but not the 480. The 480 is acting here on the head end side, and the rings here, the rings from the second stage to the balance chamber, they of course have to seal a pressure from 480 down to 120, because the balance chamber has always the suction pressure. The suction pressure in this case is 120 bar. Okay, this is critical for the design. Is challenging for the rings, but this is feasible even with this high pressure. And now I would share you the issue the trouble you can get when you have this special piston configuration. Here you see the rod load diagram over one crank, over one revolution, from 0 to 360 degree of the crankshaft. The red curve is the inertia curve of the moved parts within the frame. The blue curve is the gas load, the sum of all gas loads. That means the gas load of that area, the gas load of the balance chamber area, and the gas load of the first stage. And these are added together and creates this blue gas load distribution. And the sum of the gas load and the inertia load here in black, this is a real load acting on the crosshead pin bearing. And you see now where the critical situation is. You see, in most of the time, the load is always on the compression side. So here the rod load is in the minus area. That means compression. And there's only a small angle with a small peak load where the rod load reverses its direction. But I need this reversal of the direction. Otherwise, the hydrodynamics of the crosshead pin bearing will not work. And you will see, and all the reciprocating compressor manufacturers know that if the rod load reversal is away, meaning that this black curve would end with a peak below that green line, then we wouldn't have any rod load reversal, and then an immediate crosshead pin bearing failure would be the result. So we need a certain amount of rod load reversal, and the important information is how much rod load reversal we really need in order to have a reliable crosshead pin bearing. And therefore, we have developed some years ago a hydrodynamic program, and this is always used because it's part of our daily design program. So every sales engineer can also apply this program to assess whether the rod load reversal is enough or not. What do you see here? The black circle would be the shell, the bearing shell. The yellow strips here are the grooves which supplies fresh oil into the loaded areas. The red arrow here gives the direction, and with its length, the magnitude of the external rod load. And here the green parabola is the pressure, the hydrodynamic pressure built up created by the external rod load. The brown curves here gives an indication of areas where the oil is completely evaporated or not. And you see when the reversal takes place, the complete oil evaporates, and now it must be refilled from these two grooves, must be refilled with fresh oil. And in this bearing is with that load marginal, and in addition it must be supported by the external rod load. The external rod load pushes the small amount of oil into the loaded area. You can imagine when that red load would always be in the direction of that on the right, then there's no chance to really refill, because the load would always be in that direction. There wouldn't be any part in that direction, and then you would overload this area. Hydrodynamics could not take place, and then a bearing failure would be the result. And this is not only theory. All the compressor manufacturers know that. So a crosshead pin bearing by not enough rod load reversal is something the people of the reciprocating compressor business knows. And it can also happen not only by misdesign. For example, when you lose a discharge valve on the head end side, meaning the head end compression chamber has always discharge pressure, then typically you also lost the rod load reversal, and the consequence is typically the consequence is a failure on the crosshead pin bearing of that throw. So the reciprocating compressor engineer have to be very careful with this challenge. I mentioned it for the lubricated hydrogen compressors. There can happen some critical things with the rider bands and piston rings. And here I've collected for you some pictures of what can happen. You need to know what to do to avoid that. Here you see rider bands of hydrogen refinery compressors, big compressors. So these are compressors in the range of, the power was in the range of 2 to 4 megawatt. So big compressors, our biggest frames. Cylinder diameters in the range of, let's say, 450 to 450. So in that range. Some of them 2-stage, some of them 3-stage, depending on the suction pressure. Typically, this refinery application has a discharge pressure in the range of 120 to 150 bar. And we were faced some years ago to these issues. It looked like burned, completely overheated, and material was really removed. Here, for example, you see that there was a strong erosion in many areas of the rider bands, which were at that time not completely understood. In the meanwhile, we understood what can happen there and found the right answer to avoid that. Here's another picture. The holes in the rider bands which seem to be burned. Here at the end of the rider bands were eroded areas, material was removed. And what we also found is that for rider bands which were not completely destroyed yet, it seemed to start at the pressure relief grooves here at the end. So some ideas were immediate there that it has to do something with the flow, the leakage flow of the gas, but the leakage flow of gas typically has not the power to destroy or to erode material. So we were convinced that in addition, liquid must be present there to create this, let's say, erosion or cavitation issue. The process typically has definitely no liquid, because the source of the hydrogen is completely dry. So the only liquid we have in the system is our own oil, the oil which is used for the lubrication of the rider bands. Here's another picture what I mentioned before. Here you clearly see it. Most of the rider band looks okay, but here at the end of the pressure relief groove, we have a high amount of eroded area, which seems to be a kind of a cavitation. When you press, for example, diesel pumps for engines, when you press with high pressure to a small hole, liquid, then at the end and at the beginning, by the high velocities of the oil, cavitation can take place. And here the pictures are pretty similar. Here's another picture. This is the end gap of the piston ring. So this is not the rider band, it's a piston ring. And of course, these end gaps here are not completely closed. Even when we reach the design temperature of the compression chamber, even then we have a small amount of open gap where a leakage flow can take part or take place. And here you see there are flow signs, and again here erosion starts. And this is also a sign we typically found that at the end gaps of the piston rings also erosion was present. Here is another picture of a rider band where you see the shape of the flow pattern. You can see because oil was part of the flow, and therefore you can have an idea how the leakage flow act. Amazing was also this observation. In one of the compressors, we did not only found the issues with the rider bands, but also this pressure release bore was also strongly eroded and increased. So originally, of course, this was a small bore round, not in this, let's say, rectangular shape. It was round, and it was eroded. And when we opened the piston, indeed, we found oil in the piston. This pressure, this bore is mandatory according to API 618 because we have to make sure that the internal of the piston must always be pressure release. That is a safety device, because when you have a complete gas-tight piston which filled up with gas pressure and you bring it in a shop and open it, it can create an explosion because there's hydrogen pressure, for example, in this piston, and when you open it, this hydrogen can be released and can be ignited and can create an explosion. For other applications where you have a poisoning gas, it is even more critical, because when you open it in the shop and you have the CO or CO, for example, then people may be hurt. So this is a mandatory thing for API 618 compressor, and it makes sense. It is reasonable. And the bore was also eroded and the piston filled with oil. So from the beginning, we were convinced that the oil together with the hydrogen must create something which creates these problems. The observation of these special rider band and piston ring failures were always only be observed with hydrogen, lubricated hydrogen. We never saw it on other gases. So it seemed to be that it is linked to lubricated and hydrogen. Here are some other catastrophic rider band failures we were faced. And these problems occurred, let's say, in the mid of 2004 to 2007, not only on one compressor, but on many compressors at different installations, not in one installation, it was on different refinery installations. So it was really a technical issue which could not be linked to a certain plant. It must be an issue linked to the design of our compressor. Another picture, so always similar. We could change the material itself, So white material means we have no carbon in, it's only PTFEs with glass fiber, but all what we installed, the same issues came up. And here you see the piston. And again, even at the piston, and these pistons are typically nodular cast iron, sometimes steel, but I think in this case it will be nodular cast iron, we also found erosion areas in the range of the end caps of the piston rings. So the flow, the leakage flow, was able to remove metallic particles. And it is clear only hydrogen flow without any liquids would impossible to create these erosion. So a liquid must be part of the issue, and the only liquid we had was the oil of the lubrication. Yeah, here the technical explanation of these findings. We had too much frictional heat at rider bands created, and these created excessive oil evaporation. Why do we have too much frictional heat at rider bands? The API demands a certain amount of rider band length depending on the weight of the piston. In the API, typically horizontal compressors are used, and the rider bands have to bear the weight of the piston and the piston rod. And on basis of the weight, the rider band extension is calculated. That means here in this application, because of the high power and the relative high or big diameters, the configuration piston and piston rod were pretty heavy and creates a certain amount of mass, and this must be compensated by an amount of rider band length. Now, since there is no real hydrodynamics, we have always a mix of hydrodynamics and metallic to PTFE contact tribological system. We create heat, and this heat creates high temperature, of course, locally in contact zone. We create high temperatures. And with high temperatures, it's clear an oil evaporation, because in this contact zone we have oil. This oil will partly evaporate and will get into gaseous form, and will be part of the leakage flow of the hydrogen. So from the evaporated oil, we create a leakage flow, which is not only hydrogen flow, it is hydrogen flow with a small amount of evaporated oil. As it is gaseous, it's fine. Does not be harmful. But at areas of high flow velocities, the evaporated oil is condensing again. Of course, in these areas of the end caps of the piston rings, or in the pressure relief grooves of the rider bands, we will create high velocities. And what is special with hydrogen? Hydrogen has a very, very high speed of sound. That means the leakage flow at a hydrogen compressor at these end caps will be comparably very high, and creates a strong pressure drop, which in the end creates the recondensing of the oil. And connected with high kinetic energy of these small droplets of oil in the areas of the end caps, we realize that this energy is able to remove the material mainly from the PTFE rider bands and piston rings, but also for the metallic part of this system. Yes, I can't give you the complete story about what we did, but in the end, it was a special ring material, and this is even more important, a special rider band design to reduce the frictional heat. So here it starts with the frictional heat. Reducing the frictional heat does avoid or reduces dramatically the evaporation, and then without evaporated oil, all the other processes are no longer possible, and you don't see this erosion. So this is our solution, and since we found this solution, our standards are adjusted accordingly. Since we have introduced this, all these issues we had with the compressors in the past are gone. So now the compressors run as they should. Yeah, this is important for you whenever you have the task to compress hydrogen, high pressure or relatively high pressure above 100 bar and big power, then this issue can occur and you have to be careful with the rider band design. I mentioned it, this is the second part of the presentation. The reciprocating compressor also allows to compress gas, not only hydrogen, but also hydrogen without any oil. We got the chance some 30 years ago by the development of the PTFE as a rider band and piston ring material, base material, we have to say. So PTFE, the PTFE is a key that we can run reciprocating compressors non-lubricated. The PTFE together with let's say the liner material or the piston rod material is able to create together with the gas tribochemical reactions which creates a stable transfer film. It is a certain amount of lubrication, not by a fluid. Now the lubrication takes place just by the tribochemical reaction of the ring material, the liner material, and the gas and the pressure. So there's a complex reaction, chemical reaction, which creates a so-called transfer film on the liner surface. And this transfer film is, when you have a good tribological system, very stable. That means you can really reach very, very long lifetimes just by this tribochemical reaction in the contact zone. And this is, of course, the know-how of the ring manufacturer. Neumann Esser has an own packing and ring manufacturer here in Germany, where we have a test rig, a tribological test rig to find the optimum combination of ring material with liner or piston rod material in combination with the gas. It is very important that the gas which you are compressing is the key factor finding the right material, tribological material. As an example, nitrogen, dry, we call it bone dry nitrogen. So if it's nitrogen without any water content or very, very low water content, then it is the most difficult gas to run a recip without oil. This nitrogen seems to create or seems to avoid any stable transfer film. But even for that gas, there's a very expensive, you have to state it's an expensive material, excuse me. And with this expensive material, you even can handle this critical gas. We have compressors out with 8,000 hours, so 1 year of uninterrupted operation in nitrogen application with this material. So 1 year, 8,800 hours per year is in our business nowadays the target. If you sell a compressor, non-loop compressor, typically our clients expect 1 year of operation to without exchanging the wear parts. But we could even reach much better if the task is not so challenging. We even reach 2 hours uninterrupted operation without any oil. So the developments in the range of this rider band and ring material development is very, very dramatic. So within the last 20 years, there was made a lot of progress to create materials for given application to have lifetimes minimum 8,000 hours. Yeah, when we go up to higher pressures, and now we talk again to hydrogen, we as Non-lubricated had a lot of experience with hydrogen filling, bottle filling compressors. So the steel bottles for hydrogen are typically, in the past, were typically designed up to 220, 250 bar. And for this pressure, a non-lubricated, a reciprocating compressor can be used when you do it correctly. Above this pressure, typically nowadays we use, and this is the way how Non-lubricated works, we apply diaphragm compressors. So the pressures of the steel bottles nowadays go up to 350 bar, and for that application, we do no longer use classical reciprocating compressor, but a diaphragm compressor. To the diaphragm compressor, I come in my last part of the presentation. Yeah, when you do it as a recip, then you have some challenges. Typically, you have a high sealing pressure on the packing. And what we know, the experience up to now is a gas-tight solution for dry running can be done up to 100 bar at the packing with 1 year of continuous operation, so 8,800 hours. When you go above 100 bar, so meaning more pressure at the packing than 100 bar, then the lifetime goes down. It depends, of course, again on the material, and it also depends on the mean piston speed. So you can create a better lifetime when you reduce the mean piston speed, but reducing the mean piston speed means in the end a bigger compressor and therefore more expensive compressor. So the mean piston speed, reduces the mean piston speed is not the first choice in order to avoid that the compressor itself becomes too expensive. Yeah, and since the pressure is 250 bar, and when you applied a double acting piston, then you would see 250 bar at the packing, and the packing would not run for a very long time. And therefore, and that is not only what Non-lubricated is doing, but also our competitors, we apply the so-called tandem piston configuration as explained with the slides before. This tandem piston configuration makes sure that the pressure on the packing is much lower than the final discharge pressure. Of course, I also mentioned it before, since with this tandem piston configuration, the balance chamber is typically equipped with or connected with the suction side of the first stage. You have a high pressure differential for the second stage piston ring. That means the pressure differential on all these rings is very high. And when you have a high pressure differential, then a lot of rings are necessary. That means you get a long piston. And the other point you have to be careful is, and the PTFE is an excellent turbological material. And with fillers, typically you put glass fiber or carbon fiber in to increase the stiffness, the strength of the material. But even with these fillers, the material has the tendency to extrude when the differential pressure becomes too high. Therefore, you have to be careful with the material and the design selection of these rings to avoid this extrusion. Avoiding of high internal and external leakage rates despite light gas is also a task. You know, hydrogen is a very, very light gas. You can't compare it with, for example, CO2. That means even smallest end gaps of the ring immediately create remarkable leakage flows, which on the one side are losses, internal losses, and that means the overall efficiency reduces. But this leakage flow has, in combination with this step piston configuration, another disadvantage. By the leakage flow, which increases with increase of the wear, the intermediate pressure between the first and the second stage goes up because the reciprocating compressor needs to adjust these leakage flows. And the only chance to adjust is to reduce the pressure differential of the last stage. And then and this is our experience. After a short while, the intermediate pressure between the first and second stage increased so much that you reach the pressure relief valve of the suction side of the second stage, and you had to stop the compressor. And what we found is, even though that the rings was not completely worn out, we had to stop the compressor and change the rings. Yeah. Yes, avoiding the high internal and external leakage despite light gas, intermediate pressure offset, deteriorating with wear. That means the higher the wear, the higher the leakage flow. The higher the leakage flow, the higher the intermediate pressure shift or offset. That means in the end, a real gas-tight solution is necessary. So we need a piston ring which is more or less really gas-tight. Yeah, and this is difficult since last stage diameter is generally small. So when we talk about these bottle filling compressors, in the last stage, we had diameters between 40 to 55, 60, maximum 60 millimeters. So a relative small diameter. And for these small diameters, creating a ring system which do not allow any leakage flow, even with wear, is a tricky task. And another point is we have also to take care about is the guiding difficulties of a long and a slender tandem piston. Here you see such a configuration in a sketch. So this would be the first stage area, and this is the second stage area of the cylinder. When you put in the step piston, so here's the second stage piston with its rings, and here's the first stage with the rider band and its rings. And now what happens when the rider band have some wear? Then, of course, since the whole system is supported here and with wear, the piston of the high pressure end will tend to touch the liner of the high-end cylinder. Therefore, it's mandatory to increase the radial clearance of this piston to the liner compared to this, just by the fact that the contact of the piston itself to the liner must be avoided. Can easily be done, but if you have more clearance, extrusion is even more expectable. The smaller the clearance, the less extrusion. The higher the clearance, the more extrusion. So we need to do it in order to compensate rider band wear, but by doing it, we create more complexity in choosing the right ring sealing design. Yeah, here are some examples of these type of bottle filling compressors, and you see in the end, it depends on the suction pressure. Some have, so for example, here was relative small suction pressure. Then we needed 4 stages to create these 200 bar. In some applications, since the suction pressure was relatively high, look at here, 30 bar, then we could do it in 2 stages. This one was 210. Here in this application, the final discharge pressure was not as high. But also here, we had an application where we managed it from 19, minimum 19 bar up to 224 bar with 2 stages. So it depends on the application, mainly on the suction pressure, but also on the allowable discharge pressure. Here in this bottle filling segment, they are not as strict as the refineries in terms of the allowable discharge pressure. So in this case, we probably have discharge temperatures in the range of 140 or 150 degrees C, which would not be allowed in a refinery. Yeah, just to give you a small explanation about how it works, the piston ring. So here's a sketch. We have in that case, this is a piston. This part is a piston with a groove for the piston ring. Here, this part would be the liner. And now we have on that side, we have the high pressure, and on that side, the low pressure. What happens with the pressure? The pressure goes into this gap and into this gap, and the pressure on that surface presses the ring against that surface. The pressure on that surface presses the ring at the liner surface. In the gap here, which is, it is not a gap. By the contact pressure, you have almost no gap, but it is clear due to the fact that we have surface roughnesses, a small amount of gas flow will even take place here. And by this small amount of flow, we have a pressure reduction on that area. And therefore, when you add the pressure on that surface and the pressure on that surface, you have a relative force acting against the liner surface, and therefore a sealing effect is achieved. And here this is of course the same is true for that surface. Here also a small leakage flow, a very small leakage flow will be present, and therefore the pressure is not constant as here, and therefore we have also in this direction a relative force which presses the ring at that surface and that first surface. And that is a way how we seal by the piston ring. We reduce the amount of flow to a minimum, just in the range of the flow in these areas with the surface roughnesses. But to be honest, there is also another chance to create a leakage flow through one ring, and these are the end gaps. You must imagine that there is a gap in the piston ring and at one certain position where the gas can fully flow through the end gap to the lower pressure side. And this is with a typical ring cannot be avoided because we need a certain amount of end gap, because the PTFE has a very high thermal expansion factor. That means in the cold condition, the end gap of the ring is very, very big, and with increasing temperature until you reach the final nominal temperature, the end gap closes. But the design is done with a certain amount of safety, because the thermal expansion factor is not a fixed constant factor. You need to add some safety. So even in the condition of reaching the nominal temperature, there's a small end gap in the piston ring, and this small end gap acts as a labyrinth. So when you look into that picture, the small amounts of leakage flow here and here compared to the leakage flow in the end gap can be neglected. So the end gap creates the real leakage flow. Yeah, and here the opportunities or the possibilities we have to influence the leakage flow, especially for hydrogen. So this is the typical ring system. We have a rectangular ring and we have an end gap. This is the end. Typically, the end gap is under an angle. Just by this angle, we can reduce the leakage flow slightly. That's the reason why we use this type of end gap. But it's clear, you can see it here with the blue arrow, there is a clear leakage flow possible, like a labyrinth. So it's a labyrinth system, and there is an amount of leakage flow. Even with this type of piston ring, with the so-called overlapped end gap, even then we have a clear cross-section area where a leakage flow can occur. The only way to reduce the leakage flow to a real minimum is the use of the so-called twin rings. The twin ring these are two rings. The outer ring is seen here, and the inner ring is seen here. And the sealing goes from high pressure to low pressure in this direction. And you see then if the groove goes beyond this area of the inner ring, there is no chance of any leakage flow from that side to that side. So these rings they are called gas tight, since they do not create any remarkable leakage flow. That is a very important feature. Normally, we would like to avoid this type of ring. It's more expensive. It is more complicated, and in most of the application, it is not needed. it is even for hydrogen compressor, it is not always needed. For gases like air or nitrogen or CO2, it is completely not needed, because even knowing that this leakage flow is possible, just by the use of many rings, the leakage flow is reduced in a way that it is not really remarkable compared to the main flow. So the leakage losses can be neglected for typical application. Even for hydrogen, a refinery compressor, for example, where we have diameters of 250 to 450, which are also always lubricated, we always use these type of rings, just by the fact that these big diameters create a big flow, and the small amount, even for hydrogen, the small amount of flow is not remarkable compared to the main flow. For the bottle filling, it is a different story, because we have in the last stage diameter of 40 to 60, and then you can imagine that this hydrogen flow is a remarkable part of the main flow, and this creates this pressure shift and. So for the bottle filling, these type of rings are mandatory. We have to be sure that no remarkable leakage flow takes place. Yeah, I just explained this picture. So this would be this constellation of 1, 2, 3 rings. So here we have the compression chamber, high pressure, suction pressure, discharge pressure, and the first ring removes the pressure from that to that. So in the maximum, we have 10 bar differential reduction. The second ring takes more or less the same, and the third ring takes also more or less the same, and the last ring takes this amount of pressure. But this is only possible with these type of rings, when you have a definite leakage flow. If you use a gas type ring, then the first ring will take the complete pressure release, and all the other rings are only so-called sleepers. That means as long as the first ring is gas tight and not worn out, it will release a complete pressure. Only when this is worn out, the next one take over, and so on. And when the last one is worn out, you have to stop the compressor and exchange the rings. Here just a picture of what happens with the intermediate pressure. So here we have a 4-stage compressor configuration, both step piston configuration. First stage, second stage crank end side, third and fourth stage head end side. And we look at the leakage flows here in orange. Of course, all the piston rings creates leakage flows, which goes back to the suction side of the cylinder and must be compressed again. And with this red arrows, I give you just the idea what happens when the leakage flows goes up with the intermediate pressure. And you can see, even for this 4-stage compressor, when the leakage flows goes up, the intermediate pressure between second and third will go up, and especially the intermediate pressure between third and fourth stage will go up. And that was a problem to stop the compressor. We had rings which were not completely gas tight. The intermediate pressure went up and reached the safety valve pressure of the system. And when this is done, then you have to stop the compressor. The rings were not completely worn out. Just by the slight amount of wear and the increased leakage flow, this problem occurred. And therefore, it was clear we need here, especially in this stage and in this stage, real gas-tight rings. That is an important point. Here you see the compressor configuration, just as an example, though this was a V-type. Many of these compressors were used as a V-type. Here's the packing. Here's the first stage compression chamber with a suction and discharge valve. Here we have the balance chamber, and you see how it is managed. This room here is of wood, compressed, of course. When the piston is going up, then you would reduce this volume, and they would create pressure. And this is avoided by having a channel from this room to the suction side. So this is suction valve to the suction side of the system. So the gas is pushed through this channel to the suction side, and typically the suction valve is open to that period of time, and this pushed gas is sucked into the compression chamber, compressed and discharged. And here you see on the other end the second stage piston, which is enlarged here. So a lot of rings. We have a so-called concentric valve. This is an interesting valve, which is suction and discharge valve in one assembly. You see here from the outside, so the outer part of the valve is a suction side valve, and the inner part of this valve is a discharge. So here the gas is sucked from that side, is compressed, and then pressed into this room to the discharge side. This is you can apply it for small diameters. So I mentioned that this diameter is in the range of 40 to 60 millimeter. Then you can arrange it with this, and the main advantage is that the clearance volume is very small, that you have not to reduce the volumetric efficiency of that compression just by the effect of two suction and discharge valve and their clearance. Yeah, let's summarize the let's say the challenges and the know-how to non-lubricated reciprocating compressors for hydrogen. You typically should not go above 100 bar at the packing. This is a rule of thumb. It's valid for all reciprocating compressor manufacturers. You need to increase the radial clearance of the top tandem piston to compensate the rider band wear of the bottom tandem piston. You have to choose a cylinder and tandem piston design which is not susceptible to misalignment. Of course, any misalignment can bear the risk that the piston gets in contact with the liner, and at least up to now, up to 200 bar differential pressure at the last stage piston is feasible. To be honest, Norma ESA is working on higher pressures. We think that in the near future we can also do 400 bar discharge pressure non-lubricated with a reciprocating compressor, and must not use a diaphragm compressor. So this may, we are very optimistic that this will come. Yeah, you can use vertical V-type and horizontal compressors. Horizontal is typically not used because of the small, for the bottle filling, you typically have small compressors. So V-type and vertical are preferred. But there are also applications with lower pressures, with high flow, where you use horizontal compressors. So we have experience with up to 1.3 meter cylinder diameter and packing pressures of more than 100 bar with lifetimes above 8,000 hours uninterrupted operation. So also this is possible. Okay, now I would like to come to the third part. Yeah, the energy transition with Norma ESA. And for this energy transition, we need, at least when we look into the mobility sector, we need another type of compressor, which are also reciprocating compressors, but certain reciprocating compressors. I would like to explain these type of compressors. Yeah, content. What are the requirements for a hydrogen filling station compressor? And this will be my main focus here in this part of the presentation. What are the appropriate type of compressors due to these requirements? And the company Hofer, which has 90 years experience in that area, was bought by Norma ESA in the year 2015. And since that time, I am deeply involved in the diaphragm and hydraulically driven compressors. So the complete development, further development on that program is now in my department. And in the end, the diaphragm compressors and the hydraulically driven piston compressors will have the same level of expertise as we have with our reciprocating compressor. That's my clear target, and we are on a very good way. Yeah, what are the requirements for hydrogen filling station compressors? The compression must go up to 1000 bar, very high pressure. But this is needed. The energy density per volume is high for hydrogen, but the energy density per weight, per kilogram, is very low. That means at ambient condition, for example, you cannot store any real remarkable energy. You can only do it by increasing the pressure. And even the pressure of 200 bar, which is typically enough for a natural gas application in a car, is too less. You would not reach enough kilometers with 200 bar hydrogen. Only when you go up to, let's say, 700 to 750 bar in the tank, then you can achieve, with a fuel cell driven car, you can achieve 400 kilometers, which is nowadays assumed to be the minimum you have to reach with a car. So reaching 400 kilometer with a fuel cell driven car needs 750 bar pressure in the tank with the modern high pressure tank, which are available. Second thing is gas impurities are not allowed because, therefore it must be oil free and abrasion free, the compression. That is important because a fuel cell is, let's say they cannot accept any, especially any oil. So a lubricated surface is excluded, even when you remove with a filter the oil. Of course, 1000 bar with a lubricated compressor is possible, is easily possible, but then you had to remove the oil completely, and there are no filters, especially at that pressure range, available to remove completely the oil, and therefore a lubricated compression principle is excluded. Of course, you don't want to have any gas leakages to atmosphere. This is more economical reason. The hydrogen itself is not a climate gas, so if you do it safely, you could release some hydrogen to the atmosphere, but it is money. So non-leakage would be at least a very important feature. Explosion-proof zone 2, even zone 1 must be possible, and typically at the filling stations they demand is that low space requirements of the compressor systems are demanded. All our compressor systems we had delivered, and these are in the meanwhile far more than 100 compressor systems to filling stations. They are installed in a standard container. Yeah, and high availability is also questioned. Therefore, a robust and easy to maintain system, must be delivered. Yeah, well, what options do we have? What is it? The choice of an appropriate type of compressor. Here I gave you a rough idea of a performance map in terms of flow. Here on that axis we have the flow, cubic meter per hour, and here we have the discharge pressure. Be careful, both axes are logarithmic, so from here to here is a factor of 10 more flow, and from here to here is a factor of 10 in the pressure. So in that area, we have some very good compressors which are used in many applications. The most important one is the turbo compressor type, axial compressors, centrifugal compressors. But these type of compressors typically have a discharge pressure limit of 150 bar. We have, of course, single shaft compressors which go up to 600 bar, but the main applications are in the range of 150 bar. Screw compressors have the same range of flow. Even the pressure can go further up but be careful. They have to distinguish between the oil-flooded screw compressors and the non-lubricated screw compressors. The non-lubricated screw compressors go only up to what I know, 40 bar maximum. I think the real limit is in the range of 20 bar. And rotary compressor is also a choice, but is only applicable for small flows and small discharge pressures. But all these type of compressors do have a big disadvantage when they try to compress hydrogen. The hydrogen is a so light gas that the leakage flows of all these compressors, and these compressors has high internal leakages. The efficiency of these compressors are bad when they compress hydrogen, very bad. They are not comparable to reciprocating compressors. I just give you an example. We are nowadays in projects where we think about hydrogen pipeline compressors. For example, the Netherlands plans to replace part of their natural gas pipeline system by a hydrogen pipeline system. And in these pipeline systems now for hydrogen, they need to install reciprocating compressors instead of the turbo compressors. For natural gas, it was always a turbo compressor in the pipeline system, because for that gas, they are more effective and more reliable and more cost effective. But for hydrogen, it's impossible. A hydrogen compressor, just to give you an idea, you can compress hydrogen with a centrifugal turbo compressor. But the efficiency of this turbo compressor compared to a reciprocating compressor would be 40% more. We know it definitely because we had such a design of a hydrogen compressor done by one of the major German turbo compressor manufacturers for the application where we offered a reciprocating compressor. And from the comparison of these two offers, we know that the turbo compressor would have a 40% worse, so 40% more power efficiency. So it is it's not a choice for hydrogen. For hydrogen, we have only the choice of these compressors here. Of course, the non-lubricated piston compressors, which I mentioned it, at the moment we have 200 bar as the upper limit. More is at the moment at least not possible. We would like to extend it to 400 bar, but at the moment I would say 200 bar is the upper limit. And then we have the lubricated piston compressor. There is very high upper limit. So we have a special reciprocating compressor system which can handle even 3000 bar discharge pressure. And then, of course, we have two other systems which can handle these high pressures with, of course, smaller flows. These are the diaphragm compressors and the so-called non-lubricated hydraulically driven piston compressors. So these are reciprocating compressors which are not driven by a crank drive. They are driven by a hydraulic system. I will explain it. So for the mobility sector, we have only the choice of the diaphragm compressor or the non-lubricated hydraulically driven piston compressors. Since the non-lubricated piston compressor cannot reach the demanded 1000 bar. There's no choice. And I doubt that this system will be able to do it non-lubricated in the future. In the near future, I doubt it. 400 bar will be challenging, but 1000 bar is most likely not possible with a reasonable lifetime of the rings. Yeah, this is a typical horizontal piston compressor, reciprocating piston compressor with a frame. Here's a motor, flywheel. We have the crankshaft, the crosshead, piston rod, and here the piston. This piston is double acting, so we have a compression chamber here, and we have a compression chamber here. Here's the suction flange, and here you don't see it correctly, is a discharge flange with the valves. Here are the valves. And yeah, this is the principle of a reciprocating compressor. I have mentioned it. We can handle non-loop up to 250 bar. Above, it will be difficult. And therefore, it is not an option for hydrogen filling station. As I mentioned, we need 1000 bar discharge pressure. It could only be a choice for the first stage of a combined system, but you cannot completely do it with a classical reciprocating compressor. We have two remaining options. The first one here on the left is the diaphragm compressor. This is a 3-stage diaphragm compressor. First stage here, second stage, third stage. This is a reciprocating compressor which is not directly with the piston compressing the gas. We have between the gas and the piston, we have oil, and between the oil and the gas, we have the diaphragms. So the piston is moving the oil, and the oil is moving the diaphragm, and the diaphragm is really compressing the gas. On the other side, we have the so-called hydraulically driven piston compressors. These are reciprocating compressor piston systems, which are not driven by a crank drive. They are driven by a hydraulic system. You see here the hoses. These are the hoses for the hydraulic oil. And here we have the oil unit. So there's the electrical motor driving the oil unit. This is the oil unit. And this oil unit is pressing oil either on one side of the hydraulic piston, then the piston is moving in this direction and is compressing the gas on that side. And when the top depth center of that direction is reached, then the flow of the oil reverses. And now this oil is pushing the hydraulic piston in that direction, compressing the gas on that side. So it is a reciprocating compressor, but it is not driven by a crank drive, not mechanically driven by a crank drive. It is driven by hydraulic oil flow and oil pressure, of course. A complete different idea to do the same. Just to give you an idea, what is the let's say the speed of such a system? Here, the diaphragm compressor, for example, has a rotary speed of in the range 400, for smaller units 700. So typically these diaphragm compressors are driven between 400 and 750 RPM. Here we are in the range of 15. Double stroke, we call it double strokes. Double strokes means piston. So 15 RPM would be the equivalent speed of a compressor. And then it's clear this is the main disadvantage. You need, in principle, a factor 20 bigger cylinders to create the same flow as a diaphragm compressor, for example. And when you compare it with a real reciprocating compressor, which typically are also designed in this speed range, but have not the restrictions of the diaphragm head, they can create this with high speed and big cylinder diameters, much more flow than this type of compressor. So this type of compressor is only applicable for applications where the flow is pretty low. And at least at the moment, the flow for the hydrogen filling stations are small. So the demand is 20 kilo per hour. Typically, one car takes 5 kilo, then it's full, 5 kilo. So that means the current assumptions of hydrogen filling stations are the filling station must be able to fill up 4 hours 4 cars per hour. So these are very small compressors, and for these small flows, of course, this is an option. But it is also an option. So the same amount of flow can be handled with a diaphragm compressor too. And currently, both systems are globally used. So we have filling stations with diaphragm compressors, but we have also filling stations with hydraulically driven compressors. I can't say which are most likely the hydraulically driven piston compressors are currently more installed. So here I'm a little bit technical to explain because it's a little bit more complicated than a classical reciprocating compressor. So we have the crank drive, which is identical to a classical reciprocating compressor with a crankshaft, with a crosshead, and with a piston and piston rod. But now the difference starts. The piston is not moving against gas directly, it's moving against oil. Here, this green air room is filled with oil. And the piston rings are not sealing gas, they just seal oil. And by the movement of the piston, the oil is pushed from the bottom dead center to the top dead center against the diaphragm here, in between the gas, or here yellow, red, that is a gas. The movement of the piston moves the diaphragm from the bottom dead center to the top dead center, and by this movement, the gas is compressed. Here in the gas room, this is again identical to the reciprocating compressor. So we have a suction valve, we have a discharge valve, and when the piston is going back, we suck gas into the room, and when it's coming back, then we compress and press gas outside through the discharge valve. So here, in terms of the compression, we are pretty identical to a reciprocating compressor. But in between, we have this oil system. To make sure that the oil system works properly, we have to add something. It's clear the amount of oil is not stable because we lose some amount of oil via the piston rings, and even at least this part of the oil must be refilled. Otherwise, the room would become empty, and in the end, the diaphragm would press against the perforated plate here, and the compressor could not run. So we need to replace oil, and this is done by the so-called compensation pump. Here you see a picture of it. And this compensation pump is mounted at the non-driven end of the compressor. By this compensation pump, you always press a small amount of oil back into the head, and this amount of oil must be at least as big as the flow losses through the piston rings. And indeed, it is even more. So the oil amount in the room must be always more than the oil amount lost through the piston rings. Reason for that is we have to make sure that the diaphragm is always completely touching the diaphragm head at the end of the stroke. And by having a little bit more oil in the room, the diaphragm already touches the diaphragm head before the piston is at the top dead center. And that means the small amount of movement where the diaphragm can no longer move, the oil must be removed via this so-called oil overflow valve. So small amount of oil is not pressed over the piston rings back into the frame, but through this oil overflow valve. Only by this it is made sure that at the end of the stroke the complete gas is pressed out. Yeah, but in the end you see it is a reciprocating compressor because most of the features of the reciprocating compressors are in. And when you see a PV, a pressure volume chart of a diaphragm compressor, it is more or less identical to a PV chart of a reciprocating compressor. Yeah. Some summary to the diaphragm compressors for H2 filling stations. The diaphragm compressors meets demands for H2 filling station. It is oil-free, it is abrasion-free, it is leakage-free. It's clear, I go back. The only way external leakage would be in the area of the valves. So if the valves are not completely gas-tight sealed to the head, and as long as the diaphragm is not completely sealed at that area, we have no chance to have a leakage flow, because the diaphragm itself, it's a steel, there's a leakage to the diaphragm is impossible as long as the static seals here at the valves and here at the clamping of the diaphragm, there is no choice to have any leakage. So a diaphragm compressor is called a leakage-free compressor. Yeah, and this type of compressor was historically the first choice for this application. So Hofer started with diaphragm compressor for the hydrogen filling stations, and the experience goes back to 1990. So there were first public buses in Germany, in Hamburg, for example. We had hydrogen-driven, fuel cell-driven buses. And a Hofer compressor was used for the filling. At the airport in Munich, there was also the buses for the airport. There were also a project to do it with fuel cell buses, and also there, Hofer installed a diaphragm compressor as a compression system. Yeah, then seeing that the frequency of cars at the filling station is very low and the maintenance effort of a diaphragm compressor is higher than the maintenance effort of a hydraulically driven compressor, Hofer and therefore Norm Esser went back from the diaphragm compressor and changed over to the hydrogen filling station, the hydraulically driven compressor. As at the moment, this is a standard choice. But I'm pretty sure that in the future, the diaphragm compressor system will come back. At that point in time, where we see more cars at the filling station, then 4 cars per hour or 4 fillings per hour will not be enough. There might be 20 or 30 cars coming, and then you need more flow. And the increase of flow is limited for the hydraulically driven compressor just by the fact that we have only this 15, let's say, double strokes per minute. And therefore, we must go back to the diaphragm compressor system. Here are some examples. I mentioned it. This was at the airport in Munich. The compressor system, here you see it, was a diaphragm compressor delivered by Hofer. And the service ended in 2006, so 1997 to 2006. It ended not because the system was down. The public support was, public supported, funded fueling station, and the public support ended in 2006, and then they stopped the filling station because it was no longer economic. Yeah, suction pressure was in the range of 15 to 30 bar, and discharge pressure in that case was only 400 bar. The reason for that is for the, at least at the moment, for buses, trucks, and trains, they can handle bigger tanks. So the tanks in a bus can be bigger, and therefore the decision was to lower the tank pressure in even reaching the same kilometers. So trucks and buses, at the moment, the tanks have the pressure of 400 bar instead of 1000 bar tank. But what we hear is that even for trucks and buses, the pressure will go up to this 1000 bar, but not to that time. But you see the flow is very small. 125 standard cubic meter per hour at 30 bar is not a big deal. This is the one in Hamburg, yes, for the public buses. This was not a year, but this, I think it was even earlier. The delivery was even earlier. Again, suction pressure 12 to 16 bar, and discharge pressure in the same area, 440 bar. Flow rate is even smaller, 62 cubic meter, standard cubic meter per hour at 14 bar. And this was even enough for the buses they had. Of course, it was not the complete public fleet of Hamburg. Only a few buses were bought, and these had to be filled with this fueling station. Yeah, some word to the diaphragm compressor. system in regard to the application of hydraulic filling station. The diaphragm compressors are perfect for continuous, uninterrupted constant flow operation and for higher flow demands. Then the diaphragm lasts for years. So we know that the diaphragm compressors are running 5 or even 10 years and the diaphragm was never changed. So no real service. The only service which needed to be done was the valve service. But the valve service can be done without removing the diaphragm head. Yeah. What does a diaphragm compressor don't like? Interrupted operation. Uninterrupted, fine. Interrupted, less good. The expected lifetime of a diaphragm is then about half a year. So our experience is that when you start and stop continuously a diaphragm compressor, after half a year, you have to exchange the diaphragm. And this is just a rule of thumb. That means in some cases, it can only be a quarter year. In some cases, it can be 1 year. There is, of course, a statistic scatter, and this is not predictable. We cannot say design the diaphragm compressor in the way that it really lasts minimum half a year. This is impossible. Statistically, it will be half a year, but there is a statistical spread between at least a quarter year. And even in worst cases, you can have the situation that the diaphragm is over after 1 week. It can happen. It is not likely, but it can happen. And this is, of course, a disadvantage. Next one is the diaphragm exchange is time consuming. It takes, I don't want to say 1 day, but at least 1 shift, because you have to remove the oil, you have to remove the diaphragm head cover. There are a lot of bolts, and it's typically a heavy piece, so you need a small crane. And then you have to replace the diaphragm. You have to mantle the diaphragm head against the cover against the head, and refill with oil. So you can imagine that this is time consuming. And of course, whenever you open the diaphragm head, you lose some amount of gas. That amount of gas which is in between the closing valves on the suction and the discharge side. This gas is released to atmosphere and is away. And I mentioned it before, the diaphragm fracture, especially under the bedingung of frequent start and stop, is not plannable. Yeah, a diaphragm compressor have higher space requirement since we have a crank drive and the big diaphragm head. This is true for small flows. When the flow goes up, then it is no longer true, because then you need two hydraulically driven systems instead of 1, because otherwise you cannot handle the flow. And when you need 2 systems, then the diaphragm compressor system becomes smaller. So this is for the current flow demands of filling stations. The statement is true. The hydraulically driven system needs less space than the diaphragm compressor system. Yeah, diaphragm compressor can be flow controlled only by speed regulation with a frequency converter, and typically this is limited down to 50%. So you can control the flow from 100 to 50%. If you want to go below this value, then you need a bypass, and this is of course inefficient to a bypass solution. The hydraulically driven compressor can easily reduce the flow from 10 or 0 to 100%. So there's no limit. Yeah, let's come to the other option. This is the hydraulically driven piston compressor. For that, Hofer has, and therefore Norm Esser has a reference for this technology since 1985. It was originally developed for argon, nitrogen, and ethylene. There is a special application for what this technology was used before the hydraulic filling station. This is a so-called HIP, hydro isostatic pressures. this application is an application of a pressure of 2,000 to 3,000 bar, and with this high pressure, they improve materials by really compressing the materials to perfect strength. And this project was just adapted for the new application of hydrogen filling stations. Yeah, references are available up to 3,000 bar. That means, yeah, even at universities, even these are very small units, even 8,000 bar are built. But 3,000 bar was the original design for these compressors because the application needs the high pressure. And since 2005, we also use this system for the hydrogen filling stations. Yeah, the idea is pretty simple. So this would be a two-stage compressor, first stage, second stage. And I mentioned it already. So here, oil is filled and presses against the piston. And by the pressure and the area, we create a force. And this force is in the equilibrium with the force created by the gas pressure onto that piston. So gas pressure times that piston is always in equilibrium with oil pressure times that piston. And it's clear we have to create a reciprocating movement. That means we have to push oil either in this direction. When we reach the end position, then the flow must reversing, and now the flow must go from that side against the piston to compress the gas of the second stage. Yes, of course. As normal reciprocating compressors, we need an intermediate interstage cooler to remove the compression heat. That is the same as for normal compressors. Though instead of a crank drive, we have here an hydraulic drive. And the good thing is, with the hydraulic drive, we do not care about the so-called rod load reversal. Of course, here we have no rod load reversal, but we don't have any crosshead pin bearing which can fail. The hydraulic does not fail when the load does not reverse. So we have always compression load on the piston here and here. The load is always in this direction or here in this direction. And this is the advantage of that is, since we know that the load is always in one direction, the piston itself is not connected rigidly to the piston rod. So the piston is just touching the piston rod, and this has a big advantage, because when we need to replace the sealing elements on the piston, we just need to open here the cover with some bolts and can immediately remove the piston, can exchange the piston rings, and can introduce it back again into that area and can close it. So the maintenance work of the valves and the piston rings is very easily. You can do the maintenance within 1 hour, then it's done. Here's also an animation of the key features of this hydraulically driven reciprocating compressors. To explain again what I've already mentioned. So here's the piston. So the piston has no connection to the piston rod. You can just remove it. And you can it because the load is always compression load. There's no chance that the piston lifts off the piston rod. Yeah, we have a cooling chamber, of course. So this area where the piston is running is perfectly cooled by water. That's clear. We have frictional heat and compression heat, which is partly removed by the water. And then we have a small amount of oil. Is clear with the oil piston is not, the sealing system of the oil pistons are not completely oil tight, and this amount of oil needs to be removed out of this area. Yeah, the capacity control, I mentioned it, from 5 to 100%. It's easy because it is just the oil unit must only adjust the flow, and this can be handled. The flow of the oil must be reduced, and when we have less flow, by the oil, then of course the movement of the piston is slower, and then of course the movement of the gas piston is slower, and in the end we have less volume flow. So it is very easy. And the way how it is done by the pump. So the oil pump is driven by the electrical motor, and the flow reversal is an axial pump with an eccentric working of the pump elements, and the angle of this eccentricity can be adjusted down to 0 or even to the other direction. And by this effect, you can reverse the flow, but you can also reduce the flow. And this is easily, because it's an intrinsic part of the hydraulic system. Yeah, it is not a feature you have to add. It is there anyhow. Yeah, the key features of a hydraulically driven piston compressors, it's oil-free. It's clear the oil system is on that side. In between, we have this intermediate room, which is pressure. It's pressureless, so there's no pressure, ambient pressure, and any oil leakage and any small amount of gas leakage are going away by this leakage system. But there is no chance of oil getting into contact with the gas. Therefore, it's oil-free. It's also technically abrasion-free. Technically, we have to stay technically abrasion-free. It's clear. We have sealing elements, and these sealing elements are acting on a steel surface. They are typically the wear is very small, but a small amount of wear takes place, and this small amount of wear can also be added to the gas flow. Therefore, we call it technically abrasion-free. But from all the experience we have never get a claim that the fuel cells, in the end, the gas compressed gas is used in the fuel cells, that if any failures take place with a fuel cell just by a small amount of abrasion from the compression system. So therefore, we call it technically abrasion-free. I mentioned it already, the maintenance is simple and quick, and we have a simple flow control from 5 to 100%. We can always frequent start and stop without pressure release. So if you stop, of course, we have the pressure in the room, but as long as the sealing systems are gas tight, the pressure stays. Small amount of leakage will take place, so a small loss of leakage will take place. But you can immediately start the compressor again. It's not necessary to completely release the gas in the system. Yeah, any number of stages possible. The original equipment for one of the big filling station providers was a 3-stage configuration. The reason for the 3 stages was that the design of these filling stations was they had an intermediate pressure of 400 bar to store locally a bigger amount of gas, that they can start the car filling only with the 3rd stage. So they had the 400 bar pressure level always, and they continually pressed gas into this 400 bar level to make sure that the car filling is started with the 400 bar and the last stage, the 3rd stage. This 3rd stage was designed for these 4 cars per hour, 4 times 5 kilo, so 20 kilo per hour. The 1st and 2nd stage were designed for smaller amounts, because they were not dependent. They were not dependent on the frequency of cars. They only had to fill the 400 bar vessel in order to keep this 400 bar vessel pressure always available. Yeah, and the pressure is typically, so at the moment, all the hydrogen filling station compressor has a start pressure of 30 bar, and they go up to 1000 bar in 2 stages. So the latest designs are no longer 3 stages, but they are 2 stages. So they immediately fill the cars with a compression system. Yeah, here's some examples. Key features of a light-driven piston compressor: low space requirements, the idea for container installation, low flow requirements matching the current demand. So this system is only reasonable for low flow demands, but currently we have low flow demands for the filling stations. Yeah, here are some other installation pictures. This was in Norway, a filling station. Low suction pressure, discharge pressure 476. So this was a compressor system for trucks or buses. 60 standard cubic meter per hour. What is that? Also Norway. This is a car filling station. You see it due to the fact that we have 900 bar. This is? Yeah, this was a research installation in the Netherlands. And here we have in Berlin. So public buses in Berlin was also, yeah, there was a fund, public fund to do fuel cell buses there in 2010. And this is in Korea. Currently, most of our compressors went to Korea. So they have a public program to create a lot of hydrogen filling stations all over the country, and there's a real boom. So we sell every year many compressors just for Korea because there is this public demand, and there are many players taking part to this business. China is coming, that's for sure. We also started with selling both diaphragm compressors as well as hydrogen-driven compressors for China. Yeah, and that's one of our key customer. With this customer, we have in the meanwhile, I don't know exactly, but I would say 60 compressor installations mainly in Europe, and in Europe it is mainly Germany we have to stay, because also in Germany we have a program. The plan is to create 400 hydrogen filling stations all over in Germany. The plan is not reached yet. It should already be reached yet. Currently we have in Germany 85 or 86. So there's a long way to run to reach this 400. And my impression at the moment is that let's say the energy to reaching it is going down, because the companies which are financing that is a consortium of many companies. So Air Liquide, Linde, Mercedes-Benz, and some others are supporting this project with their money. Of course, the government also supports it with money, but there's a big amount of money which is really coming from these companies. And since they see not a huge amount of fuel cell-driven cars in Germany, let's say they are a little bit reluctant to support more filling stations. And my impression is, at least the German car manufacturer go step away from the fuel cell driven cars. They focus on the battery driven cars at the moment. But this will change, because we cannot do the cars only with battery. In the end, they will need also fuel cell cars. That's for sure. Yeah, here is a picture of our shop in Mülheim in Germany, and we have the capability to package up to 20 units in the shop itself. But in the meantime, since sometimes we need to do more than 20 units per year in the shop, we have some packagers around the facility in Mülheim, which are also trained by us to do it on behalf of us. So even 100 units per year would not be complicated for us, because we are prepared for that. And we think that it will come, not in Germany, not in Europe. I don't see any big things in Europe except for Germany, but Korea and China. The biggest market will be China, because there is a real political agenda behind the hydrogen filling station, because they would like to push the fuel cell cars in their country. Yeah, this is important. Come to the end now. This is important for you to get an idea what can be done with which type of compressor. So we have three type of compressors which come into question for non-lubricated hydrogen compressor. These are the hydraulically driven piston compressors, the diaphragm compressors, and the mechanical driven reciprocating piston compressors. We have some pressure restrictions. I mentioned it at the moment. 200 bar is the pressure limit for reciprocating compressor, non-loop. We would like to increase it to 400 bar, but I doubt that 1000 bar will be possible. So maybe 400 bar in the near future, but not more. 3000 bar is easy for the hydraulically driven piston and also for the diaphragm compressor. Both systems can handle in terms of the pressure needed, can handle it. But now you get an idea of the volume flows. The volume flow limits per compression chamber. So one compression chamber. For hydraulically driven piston compressors, we have only 15 cubic meters per hour as the possible volume flow. For diaphragm compressor, it is much more, of course. You see, with one diaphragm head, we can reach 200 cubic meter per hour. But for a reciprocating compressor, we are, of course, in a complete different world. With the reciprocating compressor, we could reach 5,000 cubic meter per hour with one compression chamber. And imagine a fourth row compressor has 8 compression chambers. So the flow of such a compressor would be 8 times 5 for 40,000 cubic meter per hour. Yeah. What are the right hydrogen filling station compression concepts? Currently, the hydraulically driven piston compressor seems to be the choice due to the small amount of fuel cell cars and due to the fact that the compression system must be used discontinuously, and this is better in terms of the lifetime of the wear parts for the hydraulically driven piston compressors. I think in the near future, the diaphragm compressor will take over the job again due to the increased amount of fuel cell cars. So in Korea, we can really say there's not only a plan to create fueling station, there's also a public plan to create cars. So it is just dramatically supported to buy a fuel cell car in Korea by the government. So there's a real increase of fuel cell cars in the streets, and we see it because these compressors we deliver to Korea are really running. That is a clear sign that cars are available. Yeah, due to this amount of fuel cell cars, ich bin gerade in Webmeeting. Ich melde mich, ja. Due to the increased amount of fuel cell cars, then we come back that the diaphragm compressor is rather continuously running, then the diaphragm compressor seems to be the better concept, and it will take over the job again. That's my assumption. Of course, it depends on how many cars are built in that areas where the hydrogen filling stations are built. And I called it the remote future. It will be a hybrid compressor concept. So it's a combination of piston and diaphragm stages. Due to the further increased amount of fuel cell cars and then continuous operation of the compressor, and the flow demands cannot be covered by a pure diaphragm compressor, and a combination of low pressure piston and high pressure diaphragm compressors might be the solution. And this looks like this system. So you see here on the right, this will be the low pressure reciprocating compressor, first stage, let's say up to 150 or 200 bar. And then the high pressure 1000 bar will be done with diaphragm heads from 200 to 1000 bar. You can in a diaphragm head, you can reach this pressure ratio of 4 easily because the cooling effect by the oil and the diaphragm is much better than in a reciprocating compressor. So this might be a future, and we as NOMS are already prepared. We already had projects not for cars, but for trains. There are also projects out where fuel cell trains in Germany, for example, we have some areas where fuel cell trains are running. And for these fuel cell trains, they need bigger amounts of flow, up to 400 bar. And for this kind of concept was offered. Unfortunately, we did not receive an order for it yet, but we are pretty convinced that it will come. Okay, and now I would like to summarize my presentation. I gave you the idea, what is needed for the hydrogen filling station, what are the requirements. Then I gave you an idea of the appropriate type of compressors due to these requirements. And our know-how, which is based on Hofer know-how, is 20 years of experience in that business. So Hofer was one of the first companies really shipping compressors for hydrogen filling stations. So I think Hofer will be, or Norma ESA will be the company with the most compressors in I'm not sure. Linde, I think Linde has also a lot. Linde and Norma ESA, these are the main players. Diaphragm compressors. So we had diaphragm compressors and hydraulically driven piston compressors. Yeah, what is the outlook? The hydraulically driven piston compressors are the current first choice. I think that diaphragm compressors come back, and when we see much more cars, many cars, then such a hybrid compressor will be the solution, the only solution. And the good thing is for us, of course, Norma ESA Group is the only company who has for all these scenarios the right choice. Okay, that's it from my side. I'm not sure how it works. I'm open for questions.
Okay, Klaus, Dr. Klaus, thank you very much for your great workshop. So we can begin now a round of questions among the participants. You can do it by the chat, or you can unmute your microphone and just go ahead and make the question. Andre Strehel, I think you have a question, Andre? Oh, sorry, I think it wasn't you. You can use the chat. Maybe it's easier since we are so many people at the same time. You can use the chat to write a question. And Andrea Fragonara has raised his hand. Andrea, please unmute your microphone and go ahead with your question. You have to unmute your microphone, Andrea, remember, before speaking. I think Andrea has had some problems with, so I think he has accidentally left the meeting. We can wait for him to connect again. I think Andrea is back in the meeting. Remember, you always have the chance to submit the question via the Telegram bot of the Plant Engineering Workshop, or the website you have with your own personalized website. You can send questions directly to the speaker.
Maybe I can make a proposal. I see a lot of questions here in the chat, and I can.
Oh, you see them because they have sent them to you privately. Then you can go ahead and reply the question.
Yeah. Maybe that is
yes, because
I just
don't have the copy.
Just go through the questions and answer it. So the first question was what is the minimum rod load reversal degrees what Norma ESA does recommend? Yeah, this is a question not simply to be answered. Maybe you will know that in the past, in the API 618, there was a demand that at least 15 degrees of angle and 3% of the main load should be the minimum. This restriction is no longer for Norma ESA, since we have this special hydrodynamic calculation tool, it is a rough idea, and in general, it works with this old API rule, but we already had in the past cases where a crosshead pin bearing failed, even though the old API 618 requirement was fulfilled. So it depends indeed on the load, and to exactly, I can't give you a real value. I can just say a good idea is the old API demand, but at least for Neumann ESSA, we check it individually. And even for very low cases, we even do not need any rod load reversal. But this is only true for lower loads. For higher loads, even our bearing will fail. For lower loads, it is possible to run the compressor without any rod load reversal. That is also possible. Yeah. So the answer is, I can't give you a fixed value, but I can say the old API 618 rule, it is a good rule of thumb. If you are in that range, in most of the cases, it will work. But a final decision we can only do, we as Neumann ESSA can only do with our hydrodynamic tool. Next question was, what is maximum cylinder diameter above which near considered special rider bands? I think this is a question to this lubricated ring failure problems. There is the diameter itself is not the key factor. We had this issue with smaller diameters and with bigger diameters. It is rather the compression power. We saw this issue only for our biggest compressor, the 1,500 kilonewton machines. For smaller compressors, we never saw these problems. So it seems to be that it is linked to the compression power. But our ring design does not care. So we analyzed the physical idea behind and found the solution. And with this solution, we can do it for smaller and for bigger cylinder diameters. It works. Our solution works for all the diameters. Okay, the next question. What is the?
I have one question here.
Yeah.
Let's see if it was sent to everyone. Yeah, maybe you can read it as well.
Yeah, which one is it in the list?
From Alberto Petenati, reciprocating compressors.
Okay.
It's about reciprocating compressors. You showed the three possible configurations: vertical, V-type, and horizontal. Yeah. Please clarify the limits of each solution.
Yeah. So vertical, again, depends on lubricated or non-lubricated, but for vertical, for horizontal, we have the limit.
Maybe you, Klaus, sorry to interrupt. Maybe you can show the diagram, go to the slide with the diagram. I don't know if that's possible.
Here, you talk about that one here.
Yeah, I guess that's the right.
Yeah.
Maybe Alberto can. Yeah.
Yeah, this is not clear. This is a diagram which I've taken from a textbook. So this, of course, don't kill me if these numbers are 100% correct. But in general, at least for the reciprocating pistons, I would say the numbers are correct. I know that turbo compressors can handle 700 bar. I worked for Siemens 20 years ago. I worked for Siemens in Germany and was in the development department of single shaft compressors. And I know that 700 bar is possible for turbo compressors. But the limits, maybe I explained it rather here.
Yeah, I think that was not the right slide. Yeah, sorry, it's a configuration: vertical, V-type, and horizontal. Yes, sorry.
Yeah. So here, this is more interesting for you. The flow. Here, I analyzed the possible flow per compression chamber. Yeah, this is of course a rule of thumb. Don't kill me if it is not 15 but 20. But just to give an idea. So the restriction here for the hydraulically driven piston compressor is clear. We have no speed. 15 revolutions per minute. It is slow, and that means you need to create the same amount of flow. You need huge cylinders, but huge cylinders will end up in huge oil pressure loads, and therefore it will create huge hydraulic drive systems. And then the hydraulic drive, and when the power of the hydraulic drive goes up, the hydraulic drive will, on the one hand side, will be very big and will also be very expensive. So there is a limit when a typical directly driven frame is driven, is more economic than a hydraulic drive. So that's a clear point here. The diaphragm compressors have their problems in the diaphragm head itself. I explain it with a movie, I think. Here, you can imagine this is the movement of the diaphragm here in this animation is much higher explained than in reality. The maximum movement of the center of the diaphragm for the biggest diaphragm is in the range of, let's say, 15 millimeters. You won't see it with your eye. That means the amount of volume which can be transported or compressed with the diaphragm is just restricted by the stiffness of the strength of the metallic diaphragm. That means for a relatively small flow, you need a huge diaphragm head, and therefore the piston diameters of a diaphragm compressor are maximum 220. Yeah, 220. So 220 millimeter is the maximum diameter of the piston. Then you create the biggest diaphragm head which is available. More is not possible. And that's the reason why also the flow demands of a diaphragm compressor are limited. It is not limited by the piston diameter. It is limited by the possibility of compressed gas with this diaphragm head. The diaphragm head becomes bigger and bigger. And for Neumann Esser, the maximum diameter is 1 meter. So the maximum possible diameter we can build is 1 meter from here to here, from the diaphragm itself. The reason for that is the metal sheets are not properly available beyond this size. And the point is, the bigger the diameter, the bigger, due to the load, the bigger will be the cover and the number and size of the bolt. So there's also a physical limit that you cannot do because the thickness or the strengths in the pieces are higher than materials are available. So this is the reason why also the floor for a diaphragm compressor is limited. Yeah, and for reciprocating compressors, there is no real limit. The only real limit is the available frame. So our biggest frame is a 1,500 kilonewton rod load frame, and I can do the cylinder as much as big as possible, as long as the load by the gas on the piston is not more than 1,500 kilonewton. Then we are at the end. Of course, one could create even frames with even more rod load, but at the moment, we and all our competitors, they all have in the same range. The biggest frame is always in this same range, so they are always in the range of 1,500 kilonewton rod load. So it seems there's not the demand to create a frame with much more rod load, and that is a limit. And the flow here is calculated with our maximum rod load. I just make an assumption, maximum rod load, and then I put a low pressure, let's say 30 bar, compressed it in that area and looked which diameter can be reached with the maximum stroke, and from that I calculated the flow. So that was a pretty simple way to do it. Yeah, I'm not sure if I completely asked the question correctly. Maybe the person can ask again. Then
maybe Alberto Petenati can send a message in the chat to everyone to confirm you have replied his question. Let's go to the next question. For hydraulically driven piston compressors, does HLP oil have any special requirements? Vicente Sanchez is asking.
No. This is a typical gear type oil. There are no special requirements needed. So it's an hydraulic oil, and the demand to the oil is not given by us as a expert on the compression principle. It is agreed with the hydraulic drive builder. So the hydraulic drive is developed together with us, but it is we as Compressor just buy the hydraulic drive, and they are the hydraulic experts, and they choose the right oil. So we as Compressor have no own demand on the oil. The quality of the oil is mainly given by the manufacturer of the hydraulic drive. But it's a typical gear type.
Another question. In case of green hydrogen production through renewables, and in particular from photovoltaic, the production can be intermittent. In case of a variable flow between 1,000 and 4,000 Newton meter cubic hour and a compression pressure of 250 bar, what would be the ideal solution technology that should be selected?
Yeah.
So
of course, it depends on the flow amount. Is it much or is it not too much? In the end, we think it will be a reciprocating compressor, especially when you talk about 250 bar, which is a pressure we can do non-lubricated. And for reciprocating compressors, we have a bunch of possibilities to economically control the flow. So we can use, of course, speed control by a frequency converter, but there are also other systems out, so-called hydrocom system, which can continuously reduce the flow from 100% to 10%. There are also pure suction valve unloading. If you have many rooms, you can reach a good flow control by just suction valve unloading. You can add clearance pockets to the cylinders. So I just would like to mention, there is not a better compressor system out than a reciprocating compressor in terms of controlling the flow without reducing the efficiency. That is the main point. You can reduce the flow of a reciprocating compressor without reducing the efficiency of the compressor. So there are many options out, and it depends on the applications. Sometimes speed control is the best choice. Speed control is excellent because the efficiency even increases slightly when you reduce the speed. But also the hydrocom system could be a perfect choice, or. So there are a lot of options, and that is we are very optimistic as Neumann Esser with the hydrogen as our future energy carrier. It must come. When they believe in this CO2 reduction, then of course there is no other choice than hydrogen, because we have to store energy. Wind will come or not, sun will shine or not, but we need continuously energy. That means we have to store energy, and the only choice to store energy I see is hydrogen. Hydrogen, bringing it to higher pressure. I think this will the only choice. And for hydrogen, there is the reciprocating compressor, the only compression principle which is perfect in all regards. It's perfect in all regards.
Thank you, Klaus. Another question: the main important things about hydrogen, which is good metals, but that compressor line, what kind of metals should be used, especially for hydrogen friability? Thanks. From Ulgen.
Can you repeat the question?
It's a bit difficult to understand. what kind of metal should be used?
Yeah.
I'm not sure about that question.
Compression principles. Again, also,
What kind?
there's almost no hydrogen compressor out in the world except for reciprocating compressors. And I include the diaphragm compressors and the hydraulically driven. For me, these three types of compressors are reciprocating compressors. And wherever hydrogen is compressed, it is more or less always a reciprocating compressor.
Yeah. And another question from Alberto Petinati, the person who asked the first question. Limits on different types of compressors have been presented quite clearly. Anyway, my question was only about reciprocating compressor and different possible configurations: vertical, V-type, and horizontal. In refineries, it is very typical to install horizontal ones, most considering maintenance issues and oil drain in case of oil lubricated machines.
Yeah, that's
so
true.
It's about the arrangement, whether vertical, V-type, and horizontal.
I can answer that. So the horizontal, it was right. In a refinery, I would say we have more or less always horizontal compressors. The reason for that is the refinery compressors are more or less always lubricated. And for the lubrication, the horizontal configuration is best because for a reciprocating compressor, you need to avoid any oil accumulation in the compression chamber. And by the horizontal placement, and you have always the suction valves on the top part of the cylinders and the discharge valve on the bottom part of the cylinders. By this configuration, you make sure that all the oil is is removed from the compression chamber through the discharge valve, and it is gone with the gas to the vessels and to the separators. When a vertical compressor lubricated is a little bit more risky, and we typically don't do that. So a vertical compressor is our preferred solution for non-lubricated compressor. But I say preferred because we have also a lot of horizontal compressors out which are non-lube. But for critical application where we know the gas is critical, we prefer the vertical compressor solution for non-lube, because now at least the rider bands are no longer loaded, because the rider bands in a vertical compressor do not see any real load because the weight is vertical and not against the rider bands. So at least we reduce the danger or the wear of the rider bands. In terms of the piston rings, the situation is the same. Vertically and horizontally arranged cylinders have, in terms of the piston rings, they see the same pressure differential, and therefore they most likely will see the same wear. But the vertical situation is the one which we use for critical non-lube application. And there's also another special type, this is so-called labyrinth type compressors. For these type of compressors where the piston rings are replaced by labyrinth type piston rings, here it is mandatory to have a vertical compressor because they have not a real rider band. The piston is supported by the crank, the crosshead, and an additional piston rod bearing. So here we cannot allow for any, let's say, radial movement by weights, and therefore we have always a vertical configuration. V-type is a mixture in between. The V-type has some advantages. Typically, it is the less expensive frame compared to vertical and horizontal. It has the advantage that the free masses of first order can be removed completely, so the foundation can be smaller. And they are, in terms of rider band load, of course, not as good as the vertical ones, but they are at least better than the horizontal ones. So for dry running application, for smaller compressors, we also use V-type compressors. But these are, to be honest, these are sometimes all political discussions. So if the available frame, the V-type frame, is in terms of the rod load the best, and the vertical one would be not as economical at the V-type, then we choose the V-type. But the main ideas, I think, are transmitted.
Thank you, Klaus. There are three more questions. I suggest or even another one, to make the reply as short as possible so that we don't run into too much time now. My question was not only about the variable hydrogen, sorry, a previous one. Regarding to the diaphragm compressor, I have been that are designed as manufacturer standard, but I need to know if there is a standard applicable as ISO or API.
Now, there is for diaphragm compressors, there is no standard available. That is the difference to reciprocating compressors. For reciprocating compressors, typically the world thinks in API 618. And even many customers have their own specifications, but in general, their main demand is the API 618, and then they add or remove from that something. For diaphragm compressors, there is no API, no ISO, nothing which gives you clear rules. So manufacturer standards is in the end is the way of producing diaphragm compressors. And we do it as Hofer. They have a standard, of course. They have their own standard. And if you ask for a compressor without any requirements, then you get the Hofer Neumann ESSA standard. If you have, of course, requirements, then we are open as Neumann ESSA to fulfill the requirements as long as they're technically feasible. That's clear.
Thank you, Klaus. Another question. DC is continuing his previous question. My question was not only about the variable hydrogen flow, but also about the fact that renewables involve numerous starts and stops during the year, 500 to 1,000. Is reciprocating piston compressor technology always good here too?
Yeah.
Thank you.
Yeah, that is, I mentioned it for the diaphragm compressor, it is not the best choice because then the lifetime of the diaphragm goes down. But for reciprocating compressor, it is not as critical. A reciprocating compressor can start and stop frequently, but our experience is, to be honest, even for the reciprocating compressor, the lifetime of the rings goes down. I give you an example. We have I mentioned it, these bottle filling compressors in my presentation, and the lifetime of these bottle filling compressors of the rings was in the range of 4,000 to 6,000 hours per year. But for the application of this, or the running hours of these application is not 8,800. So normally these compressors are used 50% of the time. So when you have a lifetime of the rings of 4,000 hours, that means 1 year of operation of the system. We had one of the compressors identically in design, equipped to a refinery, and this compressor was running 8,800 hours a year. And for this compressor, we could reach 12,000 hours, or more than double lifetime compared to the interrupted operation. So our experience is that you can extend the lifetime of the rings when you run it continuously or reduce. And the rule of thumb is that 50, of course, depending on the frequency of starts and stops. So a bottle filling compressor is start and stopped 3-4 times a day, which is a high frequency. When you say, okay, I stop the compressor once a month, it will not really influence the lifetime. But when you have such a high frequency in starting and stopping, then the rule of thumb is that the expected lifetime of the rings will only be 50% of that with uninterrupted operation.
Thank you, Klaus. Another question. Which are the materials typically used in compressors for hydrogen services? Are there any recommendations based on temperature and pressures? For example, carbon steel, IC 316L, whatever.
It depends on the pressure and temperature, of course. Our main material is 42 chromo 4, which is in terms of hydrogen embrittlement not critical, but has also very high strength. But even some of our clients demands for, let's say, for austenitic steels because concern is always the hydrogen embrittlement. The disadvantage of these austenitic steels typically is that they have not so much strength, and when we go up to higher pressures, the strength is a key factor. So we try to do, as long as the client does not demand any specific austenitic steels, we try to go with stainless steels or steels which has enough strength. 42,4, for example, is a very good solution because it has high strength, but is, in terms of hydrogen embrittlement, is a good choice.
Okay, thank you, Klaus. Another question: has Neumann Esser installed or referenced diaphragm compressors in refinery or petrochemical?
Yeah, we have. I can give you a short story. I was in India in a refinery some years ago, where we had with our big, it was a 500, so our biggest compressor, the main compressor for the refinery for their work. We had some issues, so I need to visit the customer, explaining how we've solved the issues, and then I said to them, by the way, we also bought Hofer as our diaphragm compressor manufacturer, and is now in our scope. And those people told me, and I was not aware of that. Hofer diaphragm compressor, excellent. We have a nitrogen diaphragm compressor installed for this gas system of the turbo compressor. So the gas we have the gas seals of the turbo compressors are typically sealed with nitrogen, and for this application they bought a Hofer diaphragm compressor, and they told me they didn't have touched this compressor for 5 years. This compressor ran 5 years uninterruptedly without any maintenance interval. This was, of course, a perfect, let's say, perfect comment from that clients for the diaphragm compressor. But again, I mentioned it. As long as the diaphragm compressor runs continuously, you can expect the infinitive life of the diaphragm, because its strength and it's dynamically loaded, and as long as the dynamic load goes not above the dynamic load limit of the steel, it runs forever. Only starting and stopping at different temperatures, these are loads which reduces the lifetime. So from that, just to answer the question, indeed, diaphragm compressors are also installed in refineries, and they are used, at least in that case, it was used as a nitrogen compressor for the gas system of the gas sealing system of the turbo compressor.
Thank you, Klaus. Another question: for lubricated reciprocating compressors, what is the frequency of change of oil required for hydrogen service for uninterrupted 3 years of operation?
It's a question in direction of the lubrication oil for the rings or the lubrication oil for the frame.
Because maybe the participants, RK Hadilker, can confirm. Let's go while we wait for this.
Maybe
ring lubrication.
The frame lubrication, we typically say make once a year a sample of the oil, check if the necessary, especially viscosity data, are okay. As long as these are okay, you can run with that oil, and if especially the viscosity goes down, let's say by 30% of the original, then exchange the oil. But typically you can run this oil for years. We have no combustion. We have no combustion products which deteriorates the oil. The deterioration of the oil is just given by wear parts of the bearings, and these are not critical because they are filtered.
Another question: could you provide an approximate factor to multiplied compressor cost in order to estimate its installation cost? Thank you very much.
That is difficult. I'm not the let's say commercial expert. I think that is, you can't answer. Before I say something wrong, I rather say nothing. So this is a different question. I would.
Klaus, you can reply it later because I will upload these questions for you to reply in the.
I have to discuss it with our sales manager. What rough rule of thumbs can we give? I'm not in the position to give. Of course, I have an idea of what costs the compressor system, but to give a real, let's say, accepted rule of thumb, at the moment, I'm not in the position.
I think Andrea Fragonara has already volunteered to run
Andrea Fragonara
for Patricia.
Can give an idea about that. A politically correct idea.
Yes. Another question from Daniel, and maybe this can be the last question because this is beginning to maybe too long, and we can go on with a discussion within the Plant Engineering Workshop forums, okay? 4 questions from Daniel G. First one, do you have any rough estimation cost reference to share for reciprocating compressors based on duty?
Cost?
Yeah.
Estimate
do you have,
cost? Let's say Andrea Fragonara can also answer this question.
Excellent. Yeah.
I'm not a commercial expert, so let's do it with our salespeople.
Indeed. Number 2, how do reciprocating compressors manage partial loads or flow control? Is it normally use a recirculation line for control?
No.
So partial loads or flow control.
The bypass line is typically, in most of the cases, we have a bypass to start up the compressor. There in general, a bypass line is installed. Can also be done by suction valve unloading, but bypass is in general, and bypass line is there. But to control the flow purely with the bypass, I would say we never do. It is maximally a combination. For example, you can imagine that we have suction valve unloading, and suction valve unloading is only possible in steps. That means the number of compression rooms per stage. For example, you have 2 cylinders with 4 rooms, then you can control the flow in 25% steps. So 25, 50, 75, and 100%. And then, of course, we recommend if the flow is, for example, 30%, that we go with a flow step 25%, 30 to 50%, and reduce the flow down to the 30% by a bypass. I would, if this is acceptable for smaller compressor, it might be acceptable because the loss of energy is acceptable. I even would not recommend to do it with a big compressor where we have powers of megawatt. I would always recommend do it with speed control, do it with hydrocoming, or do it with a controlled clearance pocket. Because for megawatt, even some 5% bypass control is a lot of power, which is a waste, is destroyed. So bypass control as a continuous control, I would avoid wherever it is possible.
There's one request from Daniel as well. Could you share the presentation for us? Maybe if that's okay for you, you can send it to me and I can forward to all the participants.
Yeah. I already sent you the presentation, so you have it, and you can distribute the presentation.
Okay, thank you very much. Sorry for my dog barking in the background. Could you share an email to contact you with or your team for request information about your products and solutions? Yeah, that's also a good idea.
Yeah. You can share my email.
Okay, thank you. The last question, I think that was that. I think we can. These were all the questions. So maybe we can finish the meeting here, the seminar, so that we don't make it too long. If that's okay for you, Klaus, and for the participants.
No. For me, so I was prepared to be with you this morning.
Excellent. So maybe we can go on with the discussion in the Plant Engineering Workshop. You have an option to send a question to the speaker, either via the Telegram bot or the website. So we encourage you to use any of the 2 means to contact the speaker, okay? And well, just thank you Klaus, for this wonderful seminar. I think it was very illustrative and very eye-opener. Many of the things you have mentioned about the future of transportation and so on with hydrogen. Okay, thank you very much.
Yeah, you're welcome.
Thank you. Bye-bye.
Bye-bye.